And we'll move on to our final talk of the session from Matthew Ding, our research assistant in Larry Abbott's lab at Columbia University. He will be presenting work that builds on earlier work presented by Rainer Engelken titled Quantifying Dynamic Stability and Signal Propagation, Lyapunov Spectra of Chaotic Recurrent Neural Networks. Just make sure to unmute yourself, Matthew.
Oh, sorry about that. Thank you very much for the introduction. So yeah, I'll be presenting the effects of partial connection symmetry on stability and Lyapunov spectra of recurrent neural networks. And much of this has been explained prior, but I'll go over it again, just in the context of my research to provide some more clarity, hopefully. How can I? Here. So I'll start with the motivation behind our research. There's recently been a lot more connectomic data, both on a scale of individual neurons and on a scale of brain regions. And from this arises the question of how does connectivity shape the dynamics of biological neural networks? And to study this rather complicated question, we'll consider connectivity in a common model of neurodynamics, which are recurrent neural networks. In particular, we are interested in the effect of symmetry on the autocorrelation timescales and dimensionality of the dynamics, as well as the dynamic stability, namely, how does the symmetry of the network affect the Lyapunov spectra and the stability of trajectories. Finally, we consider how partial symmetry in the initial network state affects its behavior during training and its ability to learn to generate periodic signals without input. Now, I'm going to elaborate more on what symmetry means in this context. This is a standard recurrent neural network with n-rate units and a 10 echelon linearity with a network-wide gain parameter G, which uniformly scales all of the synapse strengths inside the network. We can think of the symmetry parameterized by eta between -1 and 1 as a sort of correlation coefficient between reciprocal synapses in the recurrent neural network. As an example, an eta value of 1 would indicate total symmetry, in that if neuron A is connected to neuron B with certain strength, then the reverse connection has exactly the same strength as well. And the case of eta equals -1 is perfect antisymmetry, in which case it would have the opposite sign. Otherwise, the variance of all the entries of J, the connectivity matrix, are normalized to 1 over the square root over the network size to ensure that the spectral gap of the connectivity matrix is within a reasonable bound and varying with size. An important property to note for this network is that for a vanilla, so-called eta equals 0 network, above G equals 1, the network is chaotic. And the typical training initialization is to set a G between 1 and 1.5. We consider two cases in this following research: the strong case, in which we set G to equal 10, and the weak coupling case, in which we set G equals 1.5. And there are a few notable differences between the two cases, as I will go into. This is just a sort of review on the what Lyapunov exponents and Lyapunov spectra are. This has been explained before, but I'll go through it again. Initially, nearby conditions separate at an exponential rate, and the largest Lyapunov exponent quantifies that exponential rate of separation. If the largest Lyapunov exponent is positive, then the network is chaotic. Otherwise, it is non-chaotic. And it is also possible to define an entire Lyapunov spectrum, which is a list of the Lyapunov exponents the same length as the dimensionality of the system, which describes the transformation by the evolution of a chaotic system on a infinitesimal ball of initial points around a reference trajectory. And as a sort of illustration, I've put the visualization of such the transformation on a ball of points of a Lorentz attractor. And from the full Lyapunov spectrum, it's possible to calculate a measure of dimensionality called the Kaplan-Yorke dimensionality, which is an upper bound on the more familiar box counting dimensionality of the attractor, which indicates what fraction of phase space that the network dynamics occupy. And we can also calculate the Kolmogorov signa entropy rate as before, which quantifies the rate of growth of uncertainty due to chaotic separation of initial conditions. And just from the plots of the trajectories as a function of different eta, we can see that relative to the vanilla network, the more symmetric networks have fluctuations that are on slower timescales. And to quantify that further, we see that the autocorrelation functions of more symmetric networks decay slower relative to the vanilla networks. And in the right plot, we see that in a sort of analogous trend, the autocorrelation functions of partially antisymmetric networks decay faster than the vanilla networks. These results are also seen for networks in which the variance of the activities is held constant, meaning that even if the autocorrelation functions all start from the same initial value at 0 time lag, the trend of symmetric networks decaying slower and antisymmetric networks decaying faster will still hold. Additionally, we examine the PCA dimensionality. And to quantify this, we use a quantity called the perturbation ratio, which is incapable of interpolating between two extremes. The first of which is in that all the variance is in one dimension, in which case the perturbation ratio inverse will be 1. And the other extreme being the variance is spread equally, in which case the dimensionality will be n. And values in between 1 and n will indicate more or less extreme concentration of the variance in the first few dimensions. And we see that the trend in PCA dimensionality differs in the weak and strong coupling regime. In the PCA dimensionality decreases pretty monotonically as a function of eta around the initial eta equals 0 point, barring a few edge cases at the extremes. And in the weak coupling case of t equals 1.5, the PCA dimensionality peaks at an intermediate value of eta. As for the Lyapunov spectra, we see that we see a pretty clean trend in that more symmetric networks tend to have more curved Lyapunov spectra, indicating that more symmetric networks have both fewer positive Lyapunov exponents, and the magnitudes of those positive Lyapunov exponents are smaller. And in the antisymmetric network case, we see a similar trend in that for up to an intermediate value of minus eta, the network, more antisymmetric networks have less curved Lyapunov spectra, leading to more positive Lyapunov exponents and Lyapunov exponents with greater magnitude as well. And as a result of this, we see that in the strong coupling regime, the Kaplan-Yorke dimensionality and entropy rate also monotonically decrease as a function of eta. And the maximum Lyapunov exponent starts to decrease as a function of eta around the vanilla case, and really goes down as in the symmetric case. And taking our results to the weak coupling case of G equals 1.5, we see the similar trend for symmetric networks. And up to a certain extent, up to eta equals minus 0.3, similar trend for the antisymmetric networks here as for the strong coupling case. Eventually, due to the shape of the eigenvalue spectra of the weight matrix, networks in the antisymmetric case, in the weak coupling regime, fail to be chaotic after a certain eta, or below a certain eta threshold, after which the maximum Lyapunov exponents falls to below 0, and we see a sort of decay in the trend. A future study, I guess, would aim to control the chaoticity of the networks to see if this trend holds even in that regime. And as a result of this, the Kaplan-Yorke dimensionality and entropy rate peak at an intermediate value of eta as well. And the maximum Lyapunov exponents in the subcritical regime is linear in the symmetry parameter and peaks at the similar value as the dimensionality and entropy rate. Finally, we'll consider the training of periodic target signals. Here we use backpropagation through time, and we unroll the network for the length of one period of the target signal times a small overlap factor to ensure that the final training trajectory is non-chaotic and also periodic. As a measure of how successful the training is, we examine the convergence times, and we see that, as one might expect, more antisymmetric networks converge faster and are generally more successful at training both all of sawtooth, square, and a superposition of forward frequencies than vanilla networks or symmetric networks. Although a notable trend to indicate that is that the most antisymmetric networks are converge slowly, pretty robustly, than the eta equals minus 0.8 networks. And from here, we quantify training in a different way by setting an arbitrary success threshold. The threshold being the mean squared error below which it's the threshold of the mean squared error. And if the test error falls below that threshold before 2000 epochs, then we consider the training successful, otherwise not. And we see here also that the more anti-symmetric networks also have a higher success rate than the vanilla networks and the symmetric networks. And in conclusion, we see that with both strong coupling and weak coupling, the symmetry increasing has a pretty uniform effect of increasing the autocorrelation timescale. And likewise for antisymmetry, autocorrelation timescales decrease. For Kaplan-Yorke dimensionality, in the strong coupling case, symmetry decreases the Kaplan-Yorke dimensionality, whereas in the weak coupling case, there's a local maximum of the dimension at an intermediate value of eta, similar for the entropy rate, and with the maximum Lyapunov exponent as well. In terms of training, most of the time, backpropagation through time as a training algorithm will not suppress the chaos of a recurrent neural network. And so we only consider the weak coupling case of g equals 1.1. And in these networks, we have a greater success rate and a faster convergence time for RNNs that are anti-symmetric rather than symmetric or completely random. And a future direction in which I thought of to take this work is to not only refine the training results earlier, but also to look at further motifs that people have considered and measured in local circuits in V1 and other brain areas that incorporate multiple neurons in convergent, divergent, and chain motifs. And these sort of measured statistics may also have a pretty large effect on the stability, trainability of recurrent neural network models. And that's all. I'd like to thank Reinhard Engelken for plenty of great mentorship, Larry Abbott and Laura Leon Nijiako for helping refine and discuss this project. And we're also supported by the Gatsby Foundation, National Science Foundation, Neuronext, and the Source Foundation. And that's all.
Great. Thank you, Matthew. That was an excellent talk. You can see Reiner's great mentorship coming out for sure. I had a question. So there's time for maybe one or two quick questions. I'm going to ask a question. If you can go back to your the data figure that you showed, the last data figure that you showed about the success rates. Here you go.
Yeah.
So it looks like in each of these cases, you've got a like a peak in the success rate, albeit a small peak, that's situated like right around 0.5 for eta. Do you have an intuition for why that might be?
Well, the cause of this peak is that the training algorithm sort of fits an initial transient around the initial condition of the hidden layer state to the target signal. However, if one allows the network to run after that, we do not observe a limit cycle. We only a fixed point in the dynamics. And
okay, but why does that? Why would that cause specifically a peak in success rate there, as opposed to like kind of having a base, some sort of base success rate? Or were you about to get to that point? I'm sorry.
Well, my explanation is that because the timescales differ for different values of eta, the sort of transient length that the training algorithm has to work with may differ. And it could be the case that there's a balance between the appropriate timescale of the dynamics necessary for fitting a target signal and the appropriate transient length available to backpropagation that causes it to be most successful around eta equals 0.5.
I see.
But to sort of solidify that intuition, I would have to do more experiments.
I see.
Mm-hmm.
Great. Well, I think that that's all the time that we have for the moment. So I just want to thank again our three speakers. These were great and very